All right, now that we know a little bit about multivariable functions, we're ready to talk about partial derivatives. All right, so like I said, we're not going to be going crazy in depth with multivariable functions. I just wanted to do a brief introduction on that topic so that we can understand when there's multiple inputs involved. And now we want to talk about partial derivatives. Okay, so multivariable functions are clearly much more complicated, right, to work with. We're definitely not going to go into that in a whole lot of detail, but I encourage you to take a third semester calculus, Math 77. Maybe not, but it's a fantastic class where you really start working in three-dimensional space a lot more. But anyways, clearly they're much more complicated to work with. So it's common practice to find derivatives of multivariable functions with respect to one of the variables and treating the rest of the variables as constants. So this is the idea behind a partial derivative. It's like you're focusing on one variable and pretending that the rest are constants. Okay, kind of interesting. So for a function z equals f of x comma y, the partial derivative of f with respect to x, and this is going to be very important that we clarify which variable you're taking the derivative with respect to. Okay, that's going to be the derivative of f obtained by treating x as the variable and y as a constant. And then in the other way, the partial derivative of f with respect to y is the derivative of f obtained by treating y as the variable and x as a constant. Okay, and we have some different symbols that we use then. The symbols f with a little subscript right there, x, of x comma y. And then this kind of a cursive looking D shape, that's the partial of z with respect to x. Or you could do z sub x, or the partial of f with respect to x. That's the way that we would say that. Those are all different ways that we would represent the partial derivative of the function z equals f of x comma y with respect to x. Okay, and then similar notation could be used for partial derivative with respect to y. Okay, so the formal definition for partial derivatives, and we're actually not going to be using the limit definition, we're going to kind of just skip past that. But for the formal definition, if you have a function z equals f of x comma y, it's a function of two independent variables. And then of course, we just need to assume that all indicated limits exist for any of this to actually even make sense. Then the partial derivative of f with respect to x is, and so again, get used to this notation, that little subscript, that little subscript x right there tells you that you're taking the derivative with respect to x. Or there's this notation, it looks kind of like the dy dx notation, but we use this kind of almost like a cursive looking d for the partial derivative with respect to x. And then, yeah, it's just that limit definition where we're doing everything based on x. So it's going to be f of x plus h, and then we're just leaving the y, treating the y as if it's not involved in the limit in the derivative process. And so it's that same difference quotient, and we just let h go to 0. And then if we wanted to do the partial derivative of f with respect to y, okay, again, pay close attention to the notation. The subscript y lets you know which variable you're assuming is the variable, taking the derivative with respect to that variable, partial of f with respect to y, and then similarly, you do everything with y involved. So the h going to 0, we do y plus h in the first part of the difference quotient there. Okay? So like I said, we're not going to use these limit definitions for our partial derivatives. We're going to use the same derivative rules that we developed in chapter 4 to find partial derivatives rather than using that formal definition. But I wanted to show you that formal definition, and hopefully that makes sense. It really is just that difference quotient with the limit. And then for the x derivative, we do the x plus h in the x location. And for the y derivative, we do y plus h in the y location. So let's do an example. Let's find partial derivatives of this function. So let f of x comma y equal 4x squared minus 9xy plus 6y cubed. And we want to find the partial derivative with respect to x. And we also want to find the partial derivative with respect to y. And we'll do each one of those separately. So Interesting topic here. Be on the lookout for that notation there, because if we give you a function like this might seem somewhat familiar, or it might actually look a little bit misleading. That might look a lot like implicit differentiation to you. Remember, when we were doing implicit differentiation, we don't have to worry about product rule kind of things with the x and the y, because remember, when we're doing the derivative of this function with respect to x, you want to imagine that y is a constant. And by constant, we just mean it's some number, like a 3. And then for this one, when we're doing the derivative with respect to y, we want to assume that x is constant. So we're pretty much just focusing our efforts on one of the variables and treating the other one as if it's a constant. So it takes some getting used to. This is different than implicit differentiation. So let's go ahead and do this. We have f sub x. So the partial derivative of f with respect to x. So let's just go through and we're just going to use our normal rules. So with the 4x squared, right now we're treating x as if it's the variable. So that's just the derivative by the power rule. So the 2 would multiply down with the 4 and reduce the power by 1. Okay, then we have minus. Okay, over here, it's not a product rule because we're not doing implicit. We're treating y as if it's a constant. So what's the derivative of 9y, which is all some constant, times x? It's just going to be the constant. Okay, a little weird there. Okay, but think about that. If you wanted to take the derivative, like if the y wasn't even there, you know that the derivative of 9x is 9. Okay, but just imagine that the y is some other constant that's multiplying with the 9. And so the derivative of a constant times x is the constant. Okay, kind of interesting. Okay, and then over there with the 6y cubed, again, we're pretending that y is a constant. So don't use a power rule at all. 6y cubed, that's just some number. We're treating it as if it's a number, so the derivative of a constant is 0. All right, so the answer for the partial derivative with respect to x is just 8x minus 9y. Okay, takes some getting used to, so let's try the other version, the partial derivative with respect to y. Okay, this time we're treating x as a constant. So when we go through 4x squared, no power rule or anything there, 4x squared is just some number, and the derivative of a number is 0. Okay, then minus, okay, careful now, we're treating y like it's the variable, so the minus 9x, that's all the constant. So the derivative of a constant times y, if you're taking the derivative with respect to y, it's just the constant. Okay, and then plus, now this time, this is a variable. Y is the variable here, so we're just going to take the derivative by the power rule. So 3 multiplies down with the 6, and we get 18y and reduce the power by 1. Okay, so the answer for this one is negative 9x plus 18y squared. And that is the derivative with respect to y. Okay, interesting stuff. Almost feels like a bit of a loophole if we're taking partial derivatives and just treating the other variable as if it's a constant, but it has a ton of applications. All right, so take some getting used to. We'll do a couple more of these. I'll make a separate video to pick up on example 3.